from the first chapter what we have started. Okay, so first chapter I have started in the offline videos. This was the states of matter. Now today it will be the full detailed revision of that work. So everyone concentrate on that chapter, that is unit 5, states of matter. Okay, now we already know about the 3 general states of matter, that is solid, liquid and gases, and you have known already the 2 more states. One is plasma state and another one is BCE, Bose Einstein Condensate, BEC. So these 2 are the extra states of the matter. Now in this course, yes, the exam syllabus will be clear to you on the next, but now it was not decided. Okay. So let's concentrate on the class. Later on the upcoming classes you will be able to know about the syllabus. Next come to the plasma state and the Bose-Einstein condensate. Now the plasma state, it is found in the case of rubidium when they are cooled to a temperature that is absolute 0, and there the condensation of the molecules are there. This is called as Bose-Einstein condensate. It is found for rubidium, and the plasma state, it is the overheated state. This is known to you. Now come to the main topic about intermolecular force. Intermolecular force. This topic having few points under this. The exam will start after, I think, on the next week. It is not decided till now, but you have to follow the website. Okay, but it would be on the last of the next week, maybe, as today is, maybe it probably from the last of the next week, maybe, but not clear to us because this is not decided till now. Okay, so come to the intermolecular force. Now intermolecular forces are divided into different class. One is dipole-dipole interaction. First of all, I am writing down the details of these forces. Next one, it is ion dipolar induced ion dipole interaction. Okay. Next one, dipole induced dipole, dipole induced dipole, induced dipole interaction. Number 4 is instantaneous dipole or London force. London force, this is the number 4, and another one is there which is London force, and another one is that hydrogen bonding. Hydrogen bonding is another kind of first one, that is dipole-dipole interaction, but it is discussed in different way. Now first of all we have to come one by one about these forces. Now first of all, you know about dipole already, because dipole is the when there is the polarity difference, that is electronegativity difference in the constituent atom, and the molecule gains a dipole moment. The dipole moment having a definite direction, suppose HCl, here the net dipole moment acting on the chlorine, that is from hydrogen side to the chlorine side, but in case of CCl4 there is no net dipole moment, because the net force becomes 0 because of 2 opposite and force is there. So mu equal to 0, but here mu not equal to 0, here mu equal to 0. Mu is the expression of the dipole moment or dipolar force. Now coming to first one, that is what is dipole-dipole interaction. Dipole-dipole. Now dipole means already in the molecule it is dipole. That means for the example of HCl, just take the example of HCl. So HCl, when there is the aggregation of the HCl molecule, that means in the solution you may say, or in the general state you may say. So, in that case such type of interaction is there, HCl. So, it is a represented, that is delta plus, it is delta minus. Why this is delta? Because the total charge is not displaced. So, this is the reason, delta plus, delta minus. So, the linking, that is there is a invisible link in between the two molecules. So, this is called as dipole-dipole interaction. Now, these forces, all the intermolecular forces are responsible for the varying of the melting point, boiling point or physical characteristics. Okay. So, the physical characteristics is responsible for the intermolecular forces or varying intermolecular forces. You can see here 5 types of intermolecular forces, and they are responsible for their, sometimes it is the chemical reactivity also. Okay. So, this is the dipolar interaction. Next one, ion dipole interaction. Ion dipole interaction, here we will take 2 examples. Suppose when NaCl is dissolved in water, NaCl in water. So, as NaCl in water, we know you can already see such type of symbol, Na aqueous, Cl minus aqueous or Na plus aqueous. This signifies that the ion dipole interaction is there. How? So, when NaCl is placed in water, because of the polarity of water molecule H2O, here it is delta minus, it is delta plus, it is delta plus. This is from the dipole-dipole interaction, and for this reason later on we will know about the hydrogen bonding on water molecule. But today, now in this context, here we are dissolving sodium chloride. Now, in place of water molecule, as there is a permanent dipole moment is there, the water molecule can able to displace the sodium and chlorine atom from their bonding situation. As you know that there is no bonding, there is some electronic force or electrostatic interaction is there in between sodium and chlorine. Okay. Now, Na plus and Cl minus, there becomes a distinction and they are solvated by the water molecule or they are aquated. Now, what is solvation energy or hydration energy? If in general we will come, then it will comes the solvation energy, and if the solvent is water, then it is aquation energy. Now, when water is there, then it will be called as the hydration energy or aquation energy. So, as it is due to the stability, the Na plus getting stabilized in presence of hydrated form. So, there is a liberation of energy, and this energy will be called as hydration enthalpy or hydration energy. Clear? Hydration energy or hydration enthalpy, etc., or aquation enthalpy, because the solvent is water here. So, this energy is useful with respect to continue the process. That means, how much the sodium chloride will be dissolved, it depends on the hydration energy, because as the hydration energy will be greater, then it will helps to dissociate the bond, as there is no bond, but it will helps in the distinction of these two atoms, that is sodium, the two ions Na plus and Cl minus. So, ion dipole interaction, it is due to one permanent dipole moment and one which is electrostatic in nature, that means one is electrostatic complex. Next one, from there we will get the concept of hydration enthalpy or hydration energy. Okay. So, this is about ion dipole interaction. Later on, it is ion induced dipolar interaction. Ion induced dipole. Now, you have to know about induced dipole. What is induced dipole? So, in presence of any dipole, if one molecule get induced, that means there is the separation of charge then it will be called as induced dipole. It can be found in the solution of I minus. Suppose a solution of Ki, there it may be assumed as here is the presence of I minus because this is an electrolyte. Now I minus, in presence of I minus, if iodine is placed, I, so in presence of I minus, it will get polarized. So this type of interaction is called as ion induced dipole interaction, and we can represent it as I minus, this is I delta plus, again delta minus, this is delta minus, it will be delta 2 plus or 2 delta plus. Okay. So this is about ion induced dipole. Okay. So ion induced dipole, this is the third topic. Another one is that dipole induced dipole. So it here the presence of ion is there, I minus, but when there will be one dipole is there, and dipole when induced another neutral molecule to the dipolar form, then it will be called as the dipole induced dipole. Coming to the example, dipole induced dipole. Now here come to the example, that is carbon tetrachloride and acetone, So CCl4, it is non-polar in nature, CCl4, acetone, it is having some type of polarity because of electronegativity difference between carbon and oxygen, and carbon will get the positive charge where oxygen will be delta negative. Now as in presence of such kind of dipole is there, then in presence of acetone like substances, the CCl4 get polarized, and such type of interaction is called as dipole induced dipole interaction. And this force, that is, as they are an attractive force or interaction, that is the attractive force, the force is proportional to 1 by r to the power 6. That means the molecular distance in between these two molecules, it is depends upon that. Okay. So with respect to that, yes, this is about the ion induced dipole interaction. Okay. Another one is there, that is instantaneous dipole interaction or London force. It is generally known as London force or dispersion force. So what is London force? London force is according to the name of the scientist who first seen such type of interaction in the year of 1930. In the year of 1930, London. Fritz London is the full name of that scientist. Now what he tell, that is when a molecule is there, suppose no dipole moment, suppose oxygen, the hydrogen, not only that the dipolar molecule, also helium or the helium, neon, etc. So when there is no chance to get polarized, so that means here is the aggregation of the oxygen or the hydrogen or the methane, Cl2, etc. So when there is a aggregation of such molecules, then here is the chances of London forces. Now what is this? We have to go to the orbital representation of that. Suppose in the case of hydrogen, so here 2 electrons are there, and as there only one single orbital and the 2 electrons is there, that means here no chance to get polarized. But we know that electron cannot be represented in a specific area. Okay. So as it is not represented or as it is not identified in a single area, in a specific area, so here is a cloud is there which is called as electronic cloud, and this cloud will be spread according to the center or according to the periphery of the nucleus, that means the positive charge. So, as the dispersion of the negative charge throughout the periphery of the positive charge is not centralized, here the charge is centralized, but if there is more than 2 atoms, then the charge will not be centralized, and at that time the molecule itself become polarized, because the dispersion of the center of positive and negative charge, dispersion of positive center and negative center, dispersion of positive and negative center. This is the reason. Okay. So, this type of force which is present in the case of any non-polar molecule is called as London force, and it is not only true for such kind of element, it is also true for the noble gases. Suppose in the case of helium, sorry, hydrogen, there is only one atom, electron. In case of helium, we will get two electrons, two electrons are there. So, here also due to the displacement of the central charge delta plus, there is we can also see the kind of polarity which is called as the London force. So, it is on the neutral atom or neutral molecule. And what is the origin, that is the what is the after effect of such kind of force? Suppose one example is that when it is also depends on the surface area, the London force is also depends on the surface area. As the surface area will be large, then the interaction, the interactive force will be large. So, here is an example, the case of N-pentane and isopentane. There we can see the difference in boiling point. It is due to that effect, that is the decrease in the surface area, the isopentane having lower boiling point than that of the normal pentane. Now, just see the examples. N-pentane, it is having boiling point about 309 K, whereas in case of isobutane, it is isopentane, it is about the boiling point is 301 K. Maybe it will be very small difference, but it works further. So, it is 301 K, it is 309 K, and if we see furthermore dissociation in the bond length, that is in case of 2,2-dimethyl propane, in case of 2,2-dimethyl propane, the boiling point is found to be 283 K, 283 K. So, from there is no chance of getting polarized. So, there is the force of London is active, and for this reason there is a variation in the boiling point. It is the reason. So, that is all about the 5 types of forces, and later on we will be know about the hydrogen bonding. Okay, so, clear up to this, that means the dipole-dipole, dipole-induced dipole, ion dipole, instantaneous dipole, and the dipole-induced dipole. Okay, so next one is what is hydrogen bonding. Hydrogen bonding, it is also a kind of dipole-dipole interaction. It is also a kind of dipole-dipole interaction. So, here first take the assumption of example of HF, hydrogen fluoride. Now, there is a large difference in electronegativity, fluorine having the most electronegative element, hydrogen is an electropositive one. So, when there is a such kind of polarity, already there will be the dipole will be gained there, it will be itself work as a dipole, and this dipole moment, that is, it will also works further, that means formation of an interaction, weak interaction with the opposite pole of that molecule, of the surrounding molecule, and it is called as the hydrogen bonding. This weak interactive force is the dipole-dipole interaction, and it is also called as hydrogen bonding. Another one such type of example you can find in the water molecule also. It is of delta negative, it is delta positive, delta positive. It is also get interacted in that manner, that H, O, H. So, this is an interaction, this is also called as hydrogen bonding. Here, as it is a physical interaction, it will also affects in the molecular property, that means boiling point, the physical state also, because water itself is liquid, but when it will be weaker, that is in case of H2S, it will be in the gaseous form. Okay. So, due to hydrogen bonding, it is found in the liquid form, and also the boiling point will be higher, etc. These are the property associated with hydrogen bonding. Okay. So, this is the about interactive forces in between the molecule. Next one is that states of matter, that is impact of thermal and intermolecular interaction on the states of matter. So, thermal interaction on the states of matter. So, applying thermal condition, that means increasing the temperature, we will make the conversion of one state to another, and also the intermolecular interaction becomes weaker at that time, because the in solid here a large interactive force is associated, and for this reason they are confined to a very little space, but the intermolecular force is rather weaker in case of liquid, and it is negligible in case of gases. Okay. So, as it is in the gaseous forms, here no or very negligible amount of intermolecular force, here very little amount of intermolecular force, and here it is stronger one, and for this reason solid is found in the different crystals. Okay. That is the face centered cubic, the body centered cubic, etc. So, the crystal packing is due to the strong interactive forces, which ultimately takes them to a certain geometry. Okay. So, intermolecular interaction increases from gas to solid, and thermal energy of interaction increases from solid to gas. Next one is the gaseous states of matter. So, what are the physical characteristics of gaseous state? It do not have any specific shape, it acquires the shape of the container where they placed. They do not have definite volume, it can change by changing the temperature and pressure. Gases always form an homogeneous mixture irrespective of their nature. As example, the pure air is an homogeneous mixture. Gas rapidly diffuses in the space where they are mixed with each another, and they are highly compressible, and volume decrease by increasing pressure up to a limit. Next one, they exert the pressure equally in all direction. They have low density and have lighter than the liquids and solids. So, these are the physical characteristics of the gases. Now, what are the measurable properties of gases? The measurable properties, that is mass of the gas. So, mass of the gas, we know already what is the mole, that is the weight, that is the mass of the Avogadro number of particles. It may be atoms, it may be molecules, etc. Now, mass of the gas, the mass of the gas is basically represented in the, it is a ratio of two masses. So, number of moles equal to the weight given and the molar mass. mass of the gas divided by the molar mass. So, number of moles, it is represented as N. So, N equal to mass of the gas divided by the total mass, that is the molar mass. And the volume of the gas, what is the unit of volume? Volume can be represented as meter cube, centimeter cube, etc. And the pressure of the gas, that is the as it producing pressure equally on the wall of the container where it kept. So, the pressure is divided by the surface area of the container. So, the pressure is divided by the surface area of the container, which tells us about the pressure of the gas. Pressure, that is the total pressure exerted divided by the area of the surface. So, these are the physical parameters, that is mass, volume and pressure. So, these can be calculated. What is atmospheric pressure? Atmospheric pressure, that is called as 1 bar. Now, it can be defined as at the sea level, the height of the mercury column inside the tube is 76 centimeter or 760 millimeter. Centimeter or 760 millimeter. Here you can see a pictures like that. Here the mercury is filled, okay, and this is the vacuum and it is kept there. It is the mercury. This is called mercury barometer. So, the height of the mercury stand is 76 centimeter and it is kept at the sea level and it is at 273 K. 273 K. So, the height is given, the temperature is given, okay. And another one parameter is there, the pressure is 1 bar. So, the at 1 bar pressure and at the sea level, the pressure given by the 76 centimeter of the mercury stand at 273 Kelvin is called as the atmospheric pressure, okay. So, this is the atmospheric pressure. On the next day, I will start from the rules of the gases, okay. So, bye everyone, thank you.